Hi and welcome to this Desmos tutorial. Today we are going to take a look at quadratic and radical functions, talking about the concepts of inverses as well as reflections across the line y equals x. And all along the way we're going to look at some basic features of Desmos. A lot of these concepts and features have been covered in different videos that I've gone through. And I've done one before that covers checking inverse functions. But in this video, I'm going to start with a blank slate so that you can follow along in creating a spreadsheet from scratch all on your own. And to do that, I'll be using this Add Item button, organizing things with folders, like I've done in some of my other videos. The first thing I want is just a basic folder here for just my identity. The identity is y equals x. This will be really important for the concept of inverse functions because essentially we are reversing the inputs and outputs, or our x's and y's, and so what we'll see visually is a reflection across this line y equals x when we have our inverse function. Next folder I'll set up is for my original function. I'm just going to call this function f of x. And we can start with really a basic function, just like f of x equals x squared to start off with. The inverse of this, we would square root each side. The problem is we would get a plus or minus square root. And we can actually see what happens when we just reverse x and y by using this function notation. We can plot x equals f of y instead of y equals f of x. And there we see that reflection. The original function here was in green, and the image flipped over y equals x is in purple. We see that with these lines all being the same color, it might help to add some contrast. I'm going to actually make the identity a dashed black line. I'll make the original function just solid blue, and now this reflection is dotted purple, giving us really clear contrast there. And we can see that the original function, it does pass the vertical line test. That's great. But when we reflect it across y equals x, it does not anymore. This inverse function, it really isn't a function at all. Or I should say this reflection isn't a function. We would need to select either the top or the bottom. So the positive square root or the bottom negative square root. So it kind of brings us all the way back to the original function. This function is not one that we can find the inverse of as is. Well, you can actually add a domain restriction using braces right after that function definition and restrict it to the domain where it's one-to-one and non-decreasing, which would actually be when x is greater than or equal to 0. So starting at 0, it's level, which is not decreasing, and then it goes up from there. And now we see a reversal or a reflection across that line y equals x that is a function now. That is the top half of the square root. So I actually can now hide that, and that x equals f of y is sort of just a little test that we can do. I'll create a new folder at the bottom for my inverse function. Now the notation here is f to the -1 power. It's kind of hard to type out. What we will oftentimes do is put this in parentheses or braces or something like that to show that negative in the exponent. You don't necessarily need that if that's distracting for you. And now I'll find the inverse function. I'm going to call this g of x instead of using the proper notation with that small -1 superscript there. And here I just need to reverse the operation, so it becomes a square root function. Like I said, it would be plus or minus, but we only take the positive because we're starting with that non-decreasing portion. And now if I do some toggling, turn off the original function, here I'll make the inverse also have a different color. Let's go with a green dashed line there. I can see that that green dashed line aligns with the x equals f of y input that I used earlier. And that just shows me that I did find the correct inverse function. it aligns with this reflection of the function across y equals x. So now I can turn that one back off. I'll go back to the original function and its inverse, which we see we have different line styles for there. Now I can begin to add reflections or add transformations to the original function. For example, I can go back here and shift it to the right 5 units by just doing x minus 5 in parentheses. Now I do need to adjust that domain, change it to greater than or equal to 5. So I start at the vertex and go up. And here I would need to adjust my inverse. So thinking about what I love in math is the story of x. If we just see x one time, we can think about x as being the protagonist in the story, and there's different things happening to x. In this function I have here, where it's x minus 5 parentheses squared, the first thing that's happening in parentheses is I'm reducing x by 5. The second thing is I'm squaring the result. So thinking of that as a two-step process, reducing by 5 and squaring, I can actually find the inverse by reversing that process. Square rooting first and then increasing by 5 after the square root. And we see that making that little change there, adding the plus 5 outside the square root, gives us that nice reflection across y equals x, which we can verify with that x equals f of y input. There I have the purple dotted line aligning with the green dashed line, showing that I did find the inverse correctly. There are also other transformations we could make. I could actually shift it down by going back to the original function and placing a minus 2 after the square. Now this, in the story of x, would be the third thing that happens. I have first it's reduced by 5, then it's squared, then it's reduced by 2. So to reverse the story of x, the first thing I need to do is add the 2 to x. And you could think about the algebraic steps of solving, putting a y instead of x, putting an x over here, just like I did in this expression, solving for that y, unpacking all those steps. The very first thing I would do is add a 2 to x. That will go inside the radical. So I'd add a 2, I'd square root, and then I'd add a 5 outside. Making that adjustment, now I can see again, I've got the correct inverse. So there's a really nice way of finding inverses using that story of x. It only really works if we see x in just that one place, because if we have a multiple polynomial type expression with x showing up in multiple places, we have multiple stories to keep track of. It just doesn't work as well that way. But this is a great concept to think about that can strengthen your skills in solving for variables. Now I want to add a layer to this. There's another thing that we can do to really check our work, and I covered this in my other video on checking inverse functions, and that is using compositions. So I can find the composition of f of g of x, for example, and graph that. And I'll see that that aligns with the y equals x identity function. Let's make that a dotted black line. So that shows me that the output is just y equals x. Essentially, I'm doing some things to x, that's the original story, and then I'm undoing them. Maybe swapping the order depending on how I form my composition. Is it f of g of x or g of f of x? Keeping in mind that g of x was the inverse function there. So you're either doing the inverse first or second in that process. And all of these end up giving me that dotted line. It's just a matter of where it begins graphing the dotted line, because when we start to do compositions, we had to think about the domain of those, not only in the original function, but the composition of functions. So we'll see that line y equals x kind of starting and ending at different points there. The last concept I think that can really help you visualize these inverse functions is using the key points or adding a table in Desmos to show some points. I think it can be especially helpful if we start with a function that has both an x and a y intercept. This one does not. I'm going to actually bring it down, kind of down onto this x-axis. Actually, I'm looking at the wrong one there. So let's look at this blue one. And instead of moving it, here I went to the right by 5. Let's go to the left 2. So that would be a plus 2 there. And I need to start at -2 here. And now I have both an x and a y intercept there, and my vertex all the way down here at -2, -2. My inverse function needs some changes. The first thing when I unpack the story of x, I'm going to add 2 because that's sort of the last thing that happened. That's already there. Then the square root from the square, and then a +2 actually becomes a -2 on the outside there. So reversing the story of x to get my inverse function, we do see we've got that nice alignment with the reflection across y equals x. Now here's some key points that we can see on the blue line are its vertex where it starts. There's this intersection point. We've got a y-intercept, and then maybe we'll have one or two other points. And what we can do is use the edit list button. There is a way to add a table by adding an element, but I like the edit list because it will create a table that's linked directly to that function. And now here, it actually defaults from -2 to 2 with increments of 1, which end up being perfect points for us. But you might want to adjust the starting and ending points. What I would do then is just delete all those out, pick a starting point like my vertex here, which is -2, and then just hitting enter, -1, and enter again in that X column, it will actually continue that trend. So it will create 5 points pretty quickly using the same spacing that's used. And one of the nice things about this is if I scroll down a little, I can see the zoom fit magnifier next to that table, and it will reframe the graph to bring out that detail, sometimes a little better, sometimes not. Here what it did is it made it so that my x-axis I'm going 2, 4, and my y-axis I'm going 10, 20. So it is giving me here in these graph settings a different x and y axis to frame that potentially better. You can go back to a square zoom using the zoom square button in those graph settings, or just using the default view there. Sometimes I'll do a combination of using the magnifier but then adjusting. For example, here I would maybe want to bring out the differences between the blue and the green by zooming in the y-axis a little bit. I'll go to -5 to 10 instead of all the way up into the 20s, or even -5 to 5 is kind of looking better. It doesn't actually show all the points, so it won't go all the way to the last point in that table, but it's going to show the parts that I'm really concerned with there. Now what I can do to help understand that idea of these inverse functions is create a similar table for g of x, using that edit list, create table next to g of x, and now take the y values from the function and plug those in as your x values. So -2, -1, 2, 7, and 14 for mine. 2, 7, and 14. And what we should see is a complete reversal. So now the outputs from those gave us the original inputs that we started with. We see the reversal of y and x, just like this input x equals f of y predicts. Or we see a reflection across y equals x. Some common points are the ones that have an x and y that are equal. So if we reverse x and y and they're the same number, we're at the same point, and that's a point of intersection of the function with its inverse. Zooming out, we can see all of the points, including that 2, 14, and 14, 2. Now it's harder to visualize this reflection across y equals x now because my zoom isn't square. It's not scaled the same way with x and y. So squaring that up will actually help you see that sort of direct relationship. It's almost like a 45-degree angle right across there.